All right, so thank you for the introduction. I will talk today about DSS, which, as you can see, is short for Delta Store Semantics. Now, as you can see in the title, the context of this work is abstract garbage collection, so I'm going to start with a brief introduction to abstract garbage collection, which is basically the application of garbage collection to an abstract interpreter. To see how it works, let's say that this is the heap of your abstract interpreter, and as you are analyzing a program, certain values get allocated in this heap. I'm using lollipops here to represent values. Now, one way to ensure that an abstract interpreter always terminates is to finitize the store, to only use a finite number of addresses. But of course, that means that sometimes we're going to reuse the same address for multiple allocations. When that happens, values that get allocated at the same address are joined together, which incurs a precision loss, but it's a necessary precision loss that we have to make. It's unavoidable if we want to make sure that our abstract interpreter always terminates. And so if this goes on, then more values get allocated into the store. And well, at some point, of course, some of these addresses are no longer going to be reachable from any component of our abstract interpreter. They're going to get completely out of scope, which means that the values at these addresses become garbage. Why is this important here? Well, let's say that for our next allocation, we would allocate a value at the highlighted cell there. Well, then what would happen is that we would join the new value with the garbage value at that location, which would result in a precision loss. But in this case, it's really an unnecessary precision loss. It's an unnecessary precision loss because we're joining with a garbage value. Garbage, by definition, doesn't really need to be there, right? So if this continues, then, well, the imprecision and the garbage will propagate throughout the heap because garbage doesn't just affect your analysis results, it also actively misguides the behavior of your abstract interpreter. So how do we fix this? Well, let's go back a few steps where we were going to allocate that value. And let's say we would have triggered the garbage collection here. Well, if the garbage would have been removed, then we could have prevented the precision loss because now the value no longer needs to be joined with the garbage value. So in summary, abstract garbage collection is not really about reclaiming memory. It's about improving the precision of our abstract interpreter and therefore often also its performance. It also gives us the nice property of what we call garbage irrelevance, which basically means that the abstract interpreter doesn't need to duplicate work for different environments that only differ due to garbage bindings. The garbage doesn't really matter. The problem is, how do we integrate abstract garbage collection? Well, typically we see abstract garbage collection integrated into small step abstract interpreters, such as those from the AEM, AEC, or gamma CFA techniques. In such small step abstract interpreters, we have an expression component, an environment, a store, and a continuation. How can we do garbage collection? Well, we can use the references from the environment and the continuation as the root set of the garbage collection to garbage collect the store. The problem with these small step semantics is that we need to explicitly keep track of this continuation component. We need to abstract it, which incurs a loss in precision in the control flow behavior of our abstract interpreter, something we don't want. So these days we see that a lot of abstract interpreters instead employ big step abstract semantics. In the big step abstract semantics, we no longer have this continuation component, but instead we just have recursive evaluation rules. We have a configuration that consists out of expression environment store, and it evaluates to a value and a delta store. And specifically here, we're also following the abstract definitional interpreters approach, just like it was presented in the last presentation. And well, the reason we want to do that is because the abstract definitional interpreters or big step semantics in general, they give us perfect stack precision because we no longer need to approximate the stack ourselves. It also gives us the property of context irrelevance, which, similar to garbage irrelevance, means that we don't need to duplicate work, we don't need to duplicate evaluations for different contexts, different continuations, because in the end, these do not influence the evaluation result. So if we give a little overview here, then, well, if we take a small step abstract interpreter with abstract garbage collection, like for instance gamma CFA, then we see that we get the precision improvements from garbage collection, we get garbage irrelevance, but we don't get the perfect stack precision and context irrelevance. On the other hand, if we take a big step abstract interpreter, such as abstracting definitional interpreters, without garbage collection, we don't get any of the garbage related benefits, but we do get perfect stack precision and context irrelevance. Well, of course, this kind of raises the question, can we combine the best of both worlds here, right? So can we integrate abstract garbage collection into such a big step abstract interpreter? Well, as a first naive attempt, we could try to only take into account the references from the environment, but that wouldn't work. Why not? Well, because you might accidentally reclaim some addresses that are still going to be used later on for the continuation. In other words, the store that is returned there would not be safe to continue your evaluation with. As a second attempt, and this is what we often see done in most of the existing work, is we can add explicitly an extra component to each configuration, the set of stack references, basically all addresses are still reachable from the continuation, and then take that into account as the root set of our garbage collect. That would work, but the problem is that we're kind of throwing away some of the advantages here because we would no longer be completely context irrelevant because we are taking not directly the continuation as part of every configuration, but something that's derived from the continuation. Also, if you think about it, is it really necessary to keep the continuation bindings alive for the local evaluation? Not really. You only need them afterwards to continue evaluation with the result, right? So if you would implement garbage collection this way for ADI, then you would get the GC benefits, you would still have perfect stack precision, but you would throw out some of the context irrelevance. That's why I've put a yellow marker there. That brings us to our own approach, which we call delta store semantics, or DSS in short. The idea with delta store semantics is that we make a simple change to the big step semantics. Instead of returning an updated store as part of the result, we instead return a delta store which encodes changes with respect to the original store. Why do we do this? Well, delta stores are very flexible, and as I'll show in a moment, they allow for the integration of abstract garbage collection without taking the continuation references into account. So that gives us two advantages. We preserve context irrelevance, and secondly, because we're not taking those continuation references into account, we end up with a smaller GC root set, which means more aggressive garbage collection, which means more garbage can be collected, so more benefits. This is sometimes referred to as stackless GC. So to our knowledge, there's only one existing work out there which does something a bit similar, which is the work I've screenshotted here on heap fragment semantics. If you're familiar with the work, a heap fragment is somewhat similar to a delta store. I'm not going to go into detail about the differences and similarities here now. Instead, I'll talk about how this delta store semantics work. Let's start with just delta stores. So what is a delta store? I've put the definition of a normal store and a delta store next to each other. So a normal store maps addresses to values. A delta store, can you see the difference? It's a partial function, indeed. It's a partial function, so it only contains the bindings that have actually changed. Now, what can you do with delta stores? Well, first of all, you can apply them. If you have a computation that computes a certain delta, then you can apply the delta to the original store to reconstruct basically the updated store. Delta stores are also composable, which means that if you have a delta from one computation and a delta from the other, you can compose them into a single delta store, which captures the effects of doing one after the other. And then finally, delta stores are also joinable, and this is important in an abstract interpreter, of course, because we often end up with a non-deterministic control flow, and we might do either F or either G. Well, if we get delta A from F and delta B from G, then we can join these delta stores together into a delta store that over-approximates both possibilities. So that's delta stores. Then delta store semantics basically just expresses language semantics using these delta stores. And so we did that for a simple variation of lambda calculus. I'm not going to go into detail here. First of all, because I don't have the time for it. Second, because there's nothing really interesting to point out. This is actually very straightforward because there's still no garbage collection in these semantics. The interesting part, so I refer to the paper if you want to see the full formalization, but the interesting part I want to talk about here is the integration of garbage collection. How does that work? Well, basically on every evaluation step, what we can do is we can garbage collect a store using only references from the environment, which gives us a garbage collected store. We can evaluate that configuration. Then we can also garbage collect the delta store, meaning we end up with usually a very, very small delta store because we only have to take into account the references from the value. So we have very small or even empty delta stores in practice. And that we can use as the result of our evaluation. We can easily interleave this kind of garbage collection at every step by adding such a rule like the one shown here into the rules that I've shown on the previous slide. But again, not going to go into detail. So that looks pretty simple. Unfortunately, though, there is one situation where we have to be a bit careful, and that's the following. Let's say that in our original store, we had some address A that was bound to a value. I'm going to use a blue lollipop to present that value here. And let's say that in the garbage collection, that value got garbage collected. So A is bound to nothing in the Sigma GC store. Now then, in the evaluation, let's say that a new value got allocated at A, the pink lollipop, and so it got bound to A in the delta store, and again, for the sake of the example, let's say that it survives garbage collection. The question now is, so if we apply this delta GC to our original store, we get a store where A is bound to the pink lollipop. The question is, do we want to use that store to continue evaluation with? Well, it depends. If our evaluation happened in a tail position, then the answer is yes, because we're not interested in any of the existing bindings in Sigma for the continuation. There is no new continuation to take into account. But otherwise, if we're calling an evaluation in a non-tail position, then we may still require some of the original bindings in Sigma to continue our evaluation with. And in this case, you see that we have overwritten the blue lollipop, which may have been problematic. So what we do instead is we introduce for these non-tail calls operation, a replay operation, which, as the name suggests, replays the changes that are encoded in the delta store on the original store. So it replays the changes as if they happened on the original store. In this case, the allocation of the pink lollipop, if it had happened in the original store at address A, it would have been joined together with the blue one. Therefore, they are also joined in the resulting store after a replay. So it restores the continuation bindings. So zooming out a bit again, I've talked about two different kinds of garbage collection now. I've talked about the traditional kind of garbage collection that you see in small step abstract interpreters, as well as the stackless garbage collection that we unlock in delta store semantics with a big step abstract interpreter. A natural question then, of course, becomes how do they compare? How do they compare in terms of precision? Well, intuitively, you can probably already guess that stackless GC has an advantage. It has an advantage because it has to take less references from the, it doesn't have to take the references from the continuation into account, which means a smaller root set, which means more garbage collection. Of course, that's just intuition. As researchers, we don't trust just our intuition, we actually prove it. So we have made a proof in the ROC theorem prover that basically states this, that states that stackless GC actually indeed improves precision over the traditional GC. It states that for every big step evaluation in DSS, we also have a small step evaluation with equal or less precision. We also verified this empirically, and indeed, we look here at the results of a small step abstract interpreter with garbage collection and a big step one with garbage collection at the DSS. And if we look at the precision numbers, lower numbers are better in this column, then we see that we achieve either the same or better precision compared to the existing small step semantics. So these results also hold if we increase context sensitivity. You can look at the paper for the full evaluation. So if we go back to our overview here and we add our own approach, then we see that we can unlock the best of both worlds here. We can get all of the garbage related benefits, as well as the perfect stack precision and the context irrelevance. In fact, we're doing even better than that. We're doing better than the best of both worlds because we're unlocking an additional synergy that comes from being able to do stackless GC. Stackless GC meaning that we have to take less references into the GC root set, meaning more garbage is collected and more benefits of abstract garbage collections arise. So ideally, I could end my talk here, but unfortunately, there's also some bad news that I have to talk about. Because if you look at the performance results, you will see that we have quite a few timeouts. Something like, I think, a third of the benchmarks are just timing out. That's not great, obviously. It especially happens for programs that are a bit larger. So we can kind of say that in terms of scalability, well, DSS doesn't really scale well yet. So to see where the problem is there, well, the problem is basically that we have too many configurations. Why do we have too many configurations? Well, because every configuration has its own store, and we can have many different stores. Potentially even an infinite number of stores and continuations, in which case the abstract interpreter wouldn't even terminate. The reason I really want to mention this here, and this is something that is often overlooked when people talk about abstract garbage collection, is that abstract garbage collection makes this situation worse. It makes this situation worse because it no longer guarantees that in a single evaluation trace, our stores grow monotonically, meaning that we are no longer assured of convergence under the ascending chain condition. So what's the typical solution for this? Well, the typical solution is store widening, which joins the stores of different continuations together to improve scalability. Typically, in this setting, people employ global store widening, where basically the stores of all configurations are joined together into a single store. Unfortunately, global store widening wouldn't work well with abstract garbage collection, because if you have to put everything together in a single store, if everything that you need needs to be in that store, then you cannot remove anything from that store with garbage collection. So what we propose to do instead is what we call flow-sensitive store widening, where instead of joining the stores for all configurations, we join the stores of configurations that share the same control point. So basically the same expression and environment. In this case, for instance, the blue configurations would all be have their stores joined together, and the same for the purple ones. If we do that, then we can show that we are guaranteed to end up always with a finite number of configurations under the ascending chain condition. So our abstract interpreter always terminates. And importantly, we are able to preserve flow sensitivity, meaning we can still support strong updates as well as a limited form of abstract garbage collection. I'm saying a limited form because the widening does counteract some of the precision benefits of garbage collection. So we again formalized this DSS with flow-sensitive store widening as well as abstract garbage collection. I'm not going to go into any details here. I refer to the paper for the full formalization. And we also verified this again empirically, this time comparing DSS without store widening to DSS with store widening. If we look at the results, then we see indeed that performance is greatly improved. Of course, it does come at a cost in terms of precision, but that's a price, again, that we have to pay. And, well, we see the same results if we increase context sensitivity. What I really want to point out is how we managed to improve scalability here. If we looked at the original timeouts for DSS without store widening, we see we had timeouts in like a third of the benchmarks. Well, thanks to the store widening, we only end up with 4 more timeouts, and in fact, none when we are using a context-insensitive analysis. And so if I go back to the overview here, we can add a final approach, DSS-FS, FS for flow-sensitive store widening, where we can fix the scalability issues of DSS, of course, at some price in precision, both directly due to the widening as well as indirectly due to a slightly less efficient garbage collection. But in the end, this does allow us to formulate an approach which can combine the benefits of abstract garbage collection and push-down control flow while still maintaining scalability, which we believe is a first. So, in conclusion, I have presented delta store semantics, DSS. So DSS, the idea is that DSS makes a simple change to your big step semantics by just returning a delta store instead of a fully updated store. These delta stores are very flexible to work with, and as such, we've been able to integrate abstract garbage collection into them. Because of that, we have the best of big step abstract interpreters, abstract garbage collection, as well as the additional benefit of stackless GC. And then finally, we also made another flavor of DSS, DSS-FS, where we also added flow-sensitive store widening to recover some scalability while still maintaining most of these benefits. And on that note, I can conclude my talk. Thanks.
Do we have questions from the audience? Okay, while waiting, I can ask the first question.
Yes.
So can you comment on about the proof formalization, especially for the precision part? Because I saw there's I'm just curious about how do you quantify the precision?
Yes. So the proof is quite complicated. It's quite a long rock proof. I think we kind of underestimated the effort that goes into that. Yes. How we quantify more precise is simply by being able to prove that one value is more precise than the other using the partial order on values. But as you see, in order to make such a proof, we had to formulate a much larger theorem than what I've put in the text there, just to make sure that we were able to prove it using induction with a strong enough induction hypothesis and so on. So yeah, I don't know if that answers your question, but...
Sounds good.
Okay.
Yes. Do we have other questions?
Yes,
yes, go ahead.
I guess how much precision is lost from the final, I forget what it was called, but the final approach and then just the delta store but not optimized approach? So
you mean when we add in the widening?
Yeah.
Yeah, so if you look at the results, we see that we do lose quite a bit of precision, of course. A large part of that is because abstract garbage collection becomes slightly less effective. If you think about it, abstract garbage collection ensures that we don't have to join values together, but widening again makes it so that we join values back together. We mostly see improvements still with abstract garbage collection when you are able to do something like abstract counting and strong updates, because abstract counts are still garbage collected, and adding abstract garbage collection, even with the sensitive store widening, allows you to still have more abstract counts of one, so you can still do more strong updates. So yeah, you do lose quite a lot of precision, unfortunately, when you do this kind of flow-sensitive store widening.
Thank you very much.
Thank you. Let's thank our speaker again.